Arkadaşlar, before going into another exercise, I would like to give you properties that are very critical with discrete time Fourier transform. One of the properties is that x e to the j omega is equal to x e to the j omega plus 2 pi. So discrete time Fourier transform coefficients are periodic. Okay, they are not actually coefficients. It's like this function is periodic. You know, discrete time Fourier transform, the Fourier transform of the signal is not discrete. It is continuous function. Okay, discrete time signal, but it is aperiodic. So its Fourier transform would be periodic and continuous. Okay, so this is one property that I would like to talk about. The second property that I would like to mention is that if there is a shift in a signal, then it is going to be x e to the j omega times e to the power minus j omega and 0. Okay, so that means if there is a shift in time, it means I have to shift, I have to multiply the Fourier transform of the original function, original signal by e to the power minus j omega and 0. Okay, so the magnitude of the Fourier transform will not change, but the phase of the Fourier transform of a signal will change, will shift by n0 times omega amount. Okay, so this is something that I would like to mention here. Another property is that if there is a change like this in our signal, okay, if my x of n is this, and if I'm multiplying it with e to the power j omega 0 n, then there is a shift in frequency domain of omega 0 radians per second. Okay, for example, as an example, if I would like to perform, if I would like to multiply, let's say, if I would like to multiply my x of n, like pi n and a of n un, okay, if this is my signal, then I would do first take the Fourier transform of this one, which is 1 over 1 minus a e to the power minus j omega. Okay, and this one says now cosine pi n is equal to e to the power j pi n plus e to the power minus j pi n divided by 2, right? So this is Euler's relation, and you know it beforehand. So if I multiply my signal e to the 1 over 2 e to the power j pi n x of n plus 1 over 2 e to the power minus j pi n x of n, this is my function. Okay, this is equal to this one, and x of n is a to the power n un. Okay, a to the power n un. So by using this property, I can easily apply this property to my function, which is here 1 over 1 minus a e to the power minus j omega times 1/2, and this thing will come and be like minus pi next to my omega. You see, what does this mean? Put omega minus omega 0 in, to the places where you see omega, okay? Instead of omega, we will use omega minus omega 0. So that's why we use, if there is an e to the power j pi n, then you see my omega 0 is pi, so I put minus pi here. And I'm continuing 1/2, 1/1 minus a e to the power minus j omega plus pi. Okay, this is the Fourier transform of the signal, which is like y e to the power j omega, which is y of n is equal to cos pi n a n u n. Okay, I use this property, and then I use this property in a question which is like cos pi n a to the power n u n. Okay, another property that I would like you to remember is that if I multiply a sequence or a signal by n, it means I am taking the Fourier transform first, then performing the differentiation with respect to omega and multiply by j. Okay, this is another property that is very commonly used. So for example, if you think about, again, if it is like x of n is equal to a to the power n u n, then the Fourier transform would be 1 minus a e to the power minus j omega. If I have n times this, then I should take the derivative of this and then multiply by j. Okay, so this is how I should approach to this problem. For example, derivative of 1/1 minus a e to the power minus j omega. How do I perform this derivative? It's like derivative of the numerator, which is 0, times the denominator. This one is the denominator, minus the first one times the derivative of the denominator, which is the derivative is of 1 is 0. Derivative of this is plus a times minus j. Okay, like this one is minus a times minus j e to the power minus j omega. Okay, if you think about a e to the power minus j omega, the derivative of this one with respect to omega is like I will take this to down a times minus j, and e to the power minus j omega will stay the same. So this is a times minus j, and there is one minus here, so plus aj, and there is one minus here, again minus aj. Okay, finally, what do I have? J times minus aj divided by 1 minus a e to the power minus j omega square. Okay, let me remind you of the Fourier transform of f of x divided by g of x. F prime x times g of x minus f of x times g prime x divided by g square x, okay, or gx square. So prime means derivative. I hope you remember this property from calculus. So I applied this totally. J times J is -1 here. So A divided by 1 minus AE to the power minus J omega square is the Fourier transform of n times A to the power n un. Okay, I hope this is also clear for you. And you may watch this video in your own pace and understand what's going on. And finally, I would like to talk about the Parseval's theorem, which is x of n's square, like this is the power of a signal, is equal to 1 over 2 pi in a 2 pi integral. If I take the power of the frequency domain, Fourier transform, they are equal to each other. Okay, this is called Parseval's theorem. So if I add x of n's absolute value square and then take the integral, this is summation because this is a discrete time signal. This is integration because this is a continuous time signal. Okay, it's not continuous time, it's continuous because the time is not our variable, omega is our variable. I hope this part is also clear. Now I would like to stop at this point and continue with exercises with you.